Hi, everyone. This is the Chapter 11 edition of Principles of Scientific Inquiry, Biology and Psychology 2056 at Algoma University. This is the case studies chapter where we'll be discussing how the various components of scientific method have been translated across many disciplines to solve a variety of challenging problems in the world. Right, so the mad scientist depiction there is simply because scientists or mad scientists have generally been recognized as individuals who use science for particularly crazy and unusual tasks or solutions. So they're using science in weird ways. In this class, we're not going to look at necessarily that, but look at a diverse collection of ways that science and scientific method has indeed been used. Okay. So we'll look at 7 particular examples, the first of which is how it has been used in the discipline of philosophy. Okay, so is the philosophy of science influential? What are philosophers of science currently working on? It may seem like the philosophy that we've talked about in the course over the last while has mainly taken place, or a lot of the philosophical work for the philosophy of science has taken place a long time ago in history, right? We're talking about people who have been at work hundreds, and in some cases, many hundreds of years ago. But philosophers of science continue to be active today. There are several challenges that science faces that are challenges related to the philosophy of science. So a couple of them, for example, would be determined theory, and theory-laden data, and the issue surrounding truth. These are places where philosophers of science are actively engaged in examining these issues. So what are philosophers of science doing right now? How are they spending their time? I don't know that they're sitting on the floor in their office working on Lego, but recall that theory choice is an area where several different criteria have been discussed and explored. Just for an example, these are some of them: fit, simplicity, explanatory power. So the explanatory power of a theory is how well it can explain nature or the natural world. Coherence with other knowledge, whether the theory integrates well with different theoretical constructs as well. Predictive accuracy, we've talked about predictive accuracy as symbolizing the likely truth of a theory. If a theory is very good at predicting what will happen or what will be the case with a different collection of data that have been unexamined up until that point, that can be a sign of the theory being true. But these criteria are constantly, as we've talked about in the last lecture, subject to trade-offs, especially the first two here, fit and simplicity. So if a theory fits the data very well, oftentimes it is not the simplest of theories. So complex theories often fit data very well, but they're not necessarily true, and that's because data are noisy, and the better the fit, the more likely the model is fitting the noise as well as the actual signal in the data. Oh, testability, right? How well you can test that, etc. There's lots of these criteria. So understanding and refining how science uses different criteria to examine or prefer or choose which theory should be accepted or should be at least tentatively accepted is sort of the domain, an active domain within the philosophy of science today. All right. This is balancing criteria for theory choice, right? So balancing criteria for theory choice can be a lot like purchasing a car. If you're purchasing a car, you've probably got several criteria that you're considering. Color, maybe color shouldn't quite be the first thing on the menu, but if you're buying this car, it might be. Mileage, price, fit. So all of these things are factors that you take into accordance. These are criteria for your choice of car. The same thing, prioritizing and developing a prioritization for the different criteria for theory choice is an active domain within the field of philosophy of science. Okay. If you don't believe me that this is an active discipline, here's the official journal of the Philosophy of Science Association. This is the cover page from their webpage. So this is an ongoing place where scientists or philosophers of science publish their research, and you can see that it was constructed or initiated in 1934. You know, and it's part of a large society. It's published 5 times a year with 4 regular issues. So this is an active area where today philosophers of science are engaging in active research to improve scientific method. All right, the next example is an example of how scientific method has been used in a particular field, in the field of electronic engineering. All right, so what we have here is an analog to digital converter, sometimes called an ADC, and these have many uses in consumer electronics, audio systems, cell phones, and so on and so on. As you can imagine, in certain systems, they're going to be much smaller than is visualized here. But because of the way these are constructed, the way that they're manufactured, they have to be independently tested to examine their performance, and that's a complicated task. Conventional testing requires 2 to the 13, they're typically 13-bit converters. That's 8,192 independent tests. So imagine it's your job to test whether one little one of these coming off the assembly line is okay or works. You have to conduct 8,192 tests on it for a 13-bit converter. This took a long time previously, right? So this was a struggle. They needed a faster, cheaper way in order to figure it out. So they looked at a small number of units. So they took a few of these and they studied them in incredible detail and analyzed the data to see if there was a more efficient solution that they could take that required less work. They discovered a small number of voltages that they could run tests at that would be enough to economically test the devices. Okay. And this managed to reduce the number of required tests from 8,192 per unit to 64, so less than 1% of the original number of tests required. Okay. This is essentially using parsimony and fit and the relationship between the data, right? So we've talked about parsimony maximizing the relationships between data in a data set, and using fit as well. So this is similar. They recognized that the data were related, and therefore they could look at a subset of the data and infer performance at all or nearly all of the voltages. Okay. And so a similar process is used in the restoration of images. So in this case, if you have a blurry photo, you can get it corrected in this way by different, this is one online tool that people use to do just that. Okay, so here's a depiction of these kinds of tests. Oh, pardon me. There we go. Just trying to make that clear. Okay, a summary of how the 64 measurements capture the broader pattern. So below, and you can see I'm moving my mouse over it, this is the entire pattern with the several thousand, over 8,000 different measurements at different voltages. And you can see that the actual test reduced that to 64 measurements to capture the main pattern across those different values. Okay, so this case study is an example how expanded understanding of parsimony can increase efficiency and improve productivity. And those are 2 of the goals that we discussed early on in the course, that understanding scientific method and the elements of scientific method in great detail and carefully can accomplish, right? They can increase your efficiency, so you have to do less to get the result that you want, and increase your productivity. You can do more in the space of that time as a result. Okay. Right. So our next example is from the field of biochemistry and pharmacology. Right. So one of the main tasks that is required when you're creating new drugs is the determination of protein shape, right? So proteins have an active and prominent role in the cells and in the body. And as such, if you want to be influencing how the body's functioning, a lot of drugs will influence or pay attention or interact with proteins in the body. So determining the shape of a protein, and as visualized here, you can recognize that protein shape involves all kinds of twists and turns and different dimensional elements. So it's a very complex type of shape. So determining that shape is really important when you're creating these drugs. So the first step in doing so is called shape approximation. Okay. So using known chemical constituents, so chemical elements, so if you know what's making up the particular protein in question, and experimental electron density distribution, so actual electron scans of the protein in question, you can approximate the shape. Okay. Then you can refine the shape in the second step. This is done by matching the model to several kinds of data. First and foremost, data from X-ray diffraction. So again, a different type of imaging that you can use. Okay. There are problems, though, with error, noise, and imperfect chemical theory that we don't fully understand. So the process is imperfect. So how do we optimize that? Okay. This process can be improved by considering data from other smaller molecules that constrain possible patterns. So looking at subsets, for example, of molecules that contribute to these patterns. How much weight do the different kinds of data get in determining the most likely model for the molecule? This is, again, this issue of prioritizing different sources of data and integrating them to improve your overall theory, and it is a theory for the shape of a particular protein molecule. In 1992, a new method was proposed that creates a parsimonious, so again, using parsimony, predictively accurate model. So there's good accuracy in that. And if the model is predictably accurate, that suggests that it is capturing a lot of the important components in the actual shape of these molecules. So this optimization method, and I'll illustrate how this works, splits the data that you have into two portions, right? One containing 90% of the data. And that 90% is then used to build the model of the shape of the molecule and propose that model. And the remaining 10% is used to test the predictive accuracy of the model. So you test the model on the remaining data that did not go into building that model. This process is then repeated many times using the data in two chunks to cross-validate the model. So the better it works repetitively, the closer you are to figuring out what the true model is. The average model, or an average model, is generated after many iterations of this process. Okay. This is called the R-free method, and it's now taken over, and virtually all data in the protein data bank consist of results generated using this methodology. The unfortunate side of this story is that statistics required to accomplish this have been around for a long time, well before 1992. This is a case much like the example we gave earlier in the course, where we talked about Ghosh solving this issue of using parsimony to make better models of crop yields. We had that information a long time, and we weren't using it for quite some time. Okay, so here's an illustration of that process that I noted in the last page. So you start with all of the data, you split it up into 90 versus 10%. You use the 90% to build a model, and you use this model to predict this remaining 10% of the data. And then this process is repeated many times, sometimes thousands of times using computers. And an average model is then made from that across those thousands of iterations to get closer to the reality of the situation. Okay, this is another version of that illustrates the two different types of data that get integrated, or three in this case, this cross-correlation model, and data are used to optimize the model. So on the left, we have standard geometry. So we understand the standard geometry of molecular structures, and we get a shape from that. And then we get an initial model from electron densities that we can measure. We can measure the electron densities, and then we can get a visualization using that X-ray technique, observed intensities for protein crystals, and from the three, you can integrate to build the best model of the overall protein shape. So again, like using not just 10, so in the previous slide, I talked about splitting the data into 90% and 10%, but of course the data comes from different sources, right? Integrating these sources can be really helpful in accurately predicting this model. Okay. So the next case study is from the field of medicine, which of course is very important. Medical research needs to be highly accurate and highly efficient. There is, for an example, an ethical reason to minimize the number of individuals used in an experimental drug trial. So, you know, if, and the reason that you want to minimize that, and you might think, oh, well, shouldn't we try as many people as we can? Well, if there's any risks related to the drug, then we want to minimize any potential for harm that individuals participating in the trial could experience. So you want to start with as few people as possible to get the result you want. And of course, the other half of that ethical debate is you want this experiment to be as short as possible so that if it is effective, anyone who's been given the placebo can then be quickly given the drug, right? So you don't want people ethically to volunteer for this treatment and then for you to quickly find out that the placebo is you know, well, you know the placebo is no good, but to find out that the drug is much better than the placebo and leave some of those people on the placebo treatment. Okay. So it's also important that costs are reduced. So a smaller experiment is more efficient as well, so that you can try this many times, right? So if you have many drugs that you would like to test, it's important that these tests, which are complicated, are relatively small and cheap so that you can try it many times across many medical problems. Okay. So here's an example, a specific example. There's an experimental trial of on a serious human disease, acute leukemia, that was conducted in 1963. So this is around the time when a number of new plant-based chemotherapy drugs were coming into effect. Okay, so you had a drug treatment and a placebo. Patients were assigned randomly 2 pairs, 1 in each treatment. So you get one person, you know, a pair of individuals, and one goes into the one of the pair goes into the drug treatment, and one goes into the placebo treatment. And you can imagine pairing occurs too. So like you might have a pair of, they're not likely to be twins, but you might have a pair of people who are in the same age class, same sex, et cetera, et cetera. So they monitored how long each of them remained in remission, depending on whether they were on the drug or the placebo. And they did this for 21 pairs, or a total of 42 people. They monitored the experiment regularly, of course. And if the drug was effective, they would give it to all the patients, including those who were previously on the placebo. So they were hell-bent on getting it as efficiently as they could. 21 pairs may not seem that many, but it depends on how big, how common the drug is, and so on and so forth. Okay. So they analyzed 1 pair at a time. So if the drug were effective, they wouldn't have to give anyone else the placebo. The research used the typical frequentist test to analyze the data. So they started with 1 pair, and then they added another pair, and added another pair, etc. And they used a frequentist test to analyze those data. Now you'll remember, or maybe you'll remember, that I said that when you have a smaller data set, Bayesian statistics can make a big difference, right? So the stopping rule in this case, and remember that in frequentist tests, the stopping rule is quite subjective, came into effect when the excess of successes over failures, and now we're talking about the margin, if you're thinking about the marble experiment, was large enough to reach the 5% significance level, so a p-value of less than 0.05. They stopped after 18 patient pairs. Okay, that doesn't seem like a lot, right? But you know, it's no small number of patients, just the same, 36. Right. So in 1987, someone asked the question, you know, could we have done better given that Bayesian statistics are more efficient in handling smaller data sets, right? So someone went back and reanalyzed the same data using the Bayesian approach to see if greater efficiency could have been obtained. Using Bayesian analysis, 95% confidence in the drug's effectiveness was achieved after just 10 treatment pairs. So that's 8 fewer pairs, or 16 fewer individuals had to be analyzed and considered in order to come to the same conclusion as the original experiment did after 18 pairs. So what that means is you could have saved a number of people's a lot of pain probably, and gotten them onto the placebo much quicker, or off of the placebo and onto the drug much more quickly. Thus, the scientific method, when correctly understood and when applied as efficiently as possible using Bayesian statistics where it makes good sense to do so, can save money and save lives and simply be more ethically defensible. So if we have to defend our practices ethically, knowing carefully the scientific method and the difference between the costs and benefits of frequentist and Bayesian approaches to data analysis, we can do a better job and a more ethically defensible job of carrying out clinical trials like the one here. Okay. So the next example is from the field of sociology. You can use scientific method to assess sociological questions. So we've talked a little about science early on being criticized by a group of social scientists, but scientific methods are widely used by many social sciences to great effect, and they can do really good and interesting work. Social science and the so-called hard sciences, if you will, are really not that distinct, right? There's a considerable amount of overlap, and many social scientists recognize the real value in many of the approaches used by other scientists, particularly related to scientific method. So for example, social scientists are really interested in understanding social mobility. So just a brief rundown, social mobility means basically being able to move through or across different social strata. And they looked at it in 16 different countries. So the idea here is that if, let's say, you are born in a relatively impoverished family, social mobility is how easily or how readily people can move from one level of the social structure or social hierarchy to another. So could you become rich? How likely is this to happen? How common is this to happen? How common is it also to go from a high level to a low level? That's another aspect of social mobility. Okay. A 3x3 table looking at the father's occupation, the son's occupation in each country, with categories of social standing ranging from farm to blue collar to white collar. So a very simplified 3-category example. Okay. And the total sample size was quite large. So they had 113,556 data points contributing to this table. And they had a couple of hypotheses. Hypothesis 1, mobility flows were equal across industrialized countries. That's answering the question, are some countries better at social mobility than others? Hypothesis 2, patterns of mobility, but not amounts of mobility, are the same. So proportion, is there a greater tendency for certain groups to move and certain groups not to move, etc. Okay, these are questions that are really quite interesting questions. The frequentist test produced a complicated model with a very good p-value. The model didn't really support either H1 or H2. Remember, frequentist tests don't really address the probability of one hypothesis versus the other. Now, fair enough, though, that the two hypotheses here are not mutually exclusive. The Bayesian version supported both of the two main hypotheses, and it supported a fairly simple version of the model. So it wasn't a very good complicated model. So in this case, that's an example of how understanding Bayesian versus frequentist statistics can give you more information and perhaps prove beneficial in disentangling and finding evidence in support of different hypotheses. Okay. A second sociological example looked at the question of what drives changing obesity patterns. So obesity patterns certainly in North America have been changing considerably over the last decades, and people are interested to know what why that is, right? So the first hypothesis is that obesity is largely genetically controlled, and the second hypothesis is that it's controlled by social context. Now, I'll be honest with you. In my opinion, you don't even have to do an experiment here. When something changes rapidly over a period of decades, it's unlikely to be driven by genetic control, because genetics just don't change that rapidly over that time frame. It takes a lot longer, generations for it to change so considerably. So I think I wouldn't necessarily even say that, so in this case, I would say that the prior probability of obesity being controlled by social context is quite a bit high, and so much so that it would be an example where the prior probability would, in my mind, rule out doing such an experiment. But this experiment was indeed carried out, and perhaps it's important to do these experiments nonetheless. Okay, so genetic data were taken from about 111 youths that were aged 14 to 18, and they used principal components analysis. And what this does is it boils down genetic variation. And it basically does it in the same way that engineers got from over 8,000 tests down to 64. PCA basically gets rid of noise or redundant data, and it focuses on the clearest part of the signal in the data. So PCA can be quite useful in that way. Ooh, pardon me. About 3% of the variation in obesity was genetic, providing support for hypothesis 2, right? So very limited support for hypothesis 1, just as I suspected it would be the case, okay? The researchers also concluded that society should examine impacts such as socioeconomic status, which are correlated with obesity levels, fast food consumption, which is also a contributor. Skipping breakfast can also be important, and counterintuitively, skipping breakfast is more related to gains in obesity rather than reductions. And physical inactivity is maybe not a surprise as well. Okay. So the use of PCA, that principal components analysis, is a statistical tool for focusing analyses on that signal, right? So remember from our last lecture on parsimony, that one of the things that is desirable is to build a model that doesn't incorporate any noise from the data, but instead focuses on the signal within the data, the true signal that you're considering, or the treatment effect, if you will, at the expense of that noise. So using this PCA allowed the approach to inform changes in policies that address this issue if need be. So lots of things have happened in the wake of this kind of evidence coming to bear. People have talked about putting taxes on sugary drinks and things like that. It hasn't always come to fruition, but people are talking about them, and there's some of these initiatives are gaining steam over time as well. Okay, so next one, economics. In economics, a big question that people want to know is, are market versus state-oriented financial interventions superior? This is an excellent time to be asking this question, right? So right now, with the COVID-19 outbreak, people are asking whether governments should be stepping in to try to deal with all of the economic challenges that are coming up, or whether market forces would be the superior way to do it. Now, I'm not here to argue in favor of any of those. Certainly, there are limited market approaches that are available when basically markets shut down. But the question remains, people are always interested in whether governments that are very interventionist in their own economies, right, socialist governments, if you will, or more sort of socialist governments versus more market-based economies, governments with more market-based economies or free market-based economies, whether these are going to be a better place to weather any kinds of financial storms. So a study has concluded that how different countries behave changes based on their experiences and observations of other countries. So if we watch what's going on, it changes, and some of this, if any of you actually pay attention to economic policies around the world, you may have noticed in the recent primary lots of references by Democratic candidates like Bernie Sanders to Scandinavia and Scandinavia's behaviors economically, and pointing to those types of economic models. So people are watching and trying to choose the best system from what they see around them. The authors found support using a Bayesian approach again for the theory that decisions are primarily based on evidence and experience. So they found support for this model, that evidence and experience both factor in there, which means that we're not just dancing around doing what everybody else around us is doing, but instead looking at evidence carefully, and also our experience of what has worked and hasn't worked in recent time. So another interesting component of what they did here is they added data to the models. They added additional, so think of this in terms of, again, our parsimony model. They added different variables, right? So C, D, E, F. They made the model more complex to see if it explained what happened more accurately, right? So they added data on civil wars. So this is historical data. Membership in the Warsaw Pact after the war, recent inflation, and trade deficit. And none of these things improved the fit of the model, right? So adding extra things. And so they eliminated hypotheses like the impact of these historical factors by using the criteria for theory choice of lack of fit. And also they were needlessly making the model better, right? They weren't making the model any better. So there's no improved fit, and it's certainly getting more complex by adding these. So there was no justification for including them. Okay. So they rejected those influences as being important and built a model that was that accurately predicted the approaches countries would take. Okay. And the final example that we'll examine in this lecture is about the law. Okay. So scientific evidence is increasingly used in the field of law. We've discussed the use of DNA information to link suspects to a crime or a crime scene. In 1993, the Supreme Court of the United States ruled that federal judges must determine whether scientific evidence is reliable before it is allowed as evidence, right? So this is the reference manual on scientific evidence. So scientific evidence is not only becoming prominent in the law, but people are making sure that literacy is there for these judges, and federal judges have to be scientifically literate in such a way as to determine whether the scientific evidence being presented in a trial is reliable before it is even allowed as evidence. So that cranks up the requirement of scientific literacy for the judiciary, which is quite an interesting reality. So, you know, you don't necessarily imagine that people sitting as federal judges have to be very well informed on science, but they do. Okay, let me just move this guy. We have also discussed how reversed conditional probabilities can be misused under the law. So we discussed the difference between the probability of a match with evidence, match of evidence sort of between a suspect and at the crime scene, given innocence versus the probability of innocence given match, and how those probabilities can be different. And how can the law be reconciled with probabilistic conclusions that emerge sometimes from scientific approaches? This is a question that's an interesting question that I'm not sure there's a good answer for, right? So here's an example. What is acceptable for conviction? The probability of innocence given a match is 0.02, or the probability of innocence given a match is 0.06, right? So we have a way to numerically inform evidence in this way, or the probability of innocence. But at what point, so at no point is there any way to determine whether this, what number matches up with beyond a reasonable doubt, which is usually the criteria that is adopted in scientific or in the law, right? So you have to determine guilt on the basis of confidence beyond a reasonable doubt. Well, do these probabilities, probability of 2% or 6%, which one, if any, do we use if we can inform probabilities that way? And certainly with DNA evidence, we can get a p-value like this. We can get a probability, or not a p-value, but in this case, it's a Bayesian probability. So we can get a probability of innocence, but we can't tell the judiciary or the field of law what to accord, how to take those numbers and convert them to beyond a reasonable doubt. But make no mistake, there should be some clarity around that issue, and there is not. Okay, here's another example. So reasonable suspicion is another sort of thing that can be numerically informed. So in this case, people at airports can do drug searches, given that they have a reasonable suspicion. But what does reasonable suspicion mean, right? Let's examine it from a probability perspective. The prior probability of that someone is a drug courier, based on the evidence that we have, is quite low, right? It's 0.00001, right? So it's way less than 0.01%. So very low, okay? Profiling for couriers, so the ability for people to watch, is about 70% accurate, right? Which sounds pretty good on the surface. And 1 in 1,000 travelers match the profile, right? So that means a likelihood ratio can be calculated directly, okay? This means the odds of a person matching the profile being a courier can be calculated directly using the Bayesian formula. And it's 0.07, or probability, if you want to be more specific, of the person that matches the profile actually being a drug courier of being 6.5%. So it's much lower than that 70% accuracy, simply because the prior probability of someone being a drug courier is quite low, right? So the accuracy means that there's going to be a lot of false positives, right? Where people are not drug couriers and they're being searched, right? May I draw your attention to this very unlikely scenario? I don't know if this woman matches the profile or not, but it seems very unlikely that she would be a drug courier. Maybe if she has a terrible 401k, I don't know. All right, actual success rate was reported as 4%. So is this beyond a reasonable suspicion? If this were challenged in a court of law by someone who had been stopped and searched, what would the outcome be? Would they be able to sue on the basis of a violation of reasonable suspicion? 4% doesn't seem like a lot for reasonable suspicion. So this can, again, scientific approaches can inform these processes, but it's up to the law to apply them and determine how to apply them. And that's not an easy task, but it can be useful, right? The fact that we can calculate this should be quite useful. It gives us the information to make careful decisions on this type of thing, and allows us to make those kinds of decisions regularly. Okay. So here's an example of how it was used, or this information can be used. New Jersey lawmakers to announce opposition to full body scanning at airports. If this could potentially be, this is just a screen capture of the news from 2010. But ultimately, this is an example where it may be that individuals use data to figure out that it was not beyond a reasonable doubt based on the probability of success from people who are profiling, people going through the airport. Okay. Let me just pull this away. There are other challenges in using scientific evidence in law. Can anyone here guess them? Well, I'm going to just go out on a limb and say no one's going to answer me. So here's an example of what could go wrong, right? Are juries going to understand this kind of thing? Are juries going to understand a 6% probability of innocence given a match? Will they be able to carefully apply the correct criteria, or should, in cases like that, probability, a standard be adopted that takes the jury's opinion out of the matter? Takes the subjectivity out of the matter. I don't know. I don't have an answer for that. But many jurors will not be scientifically literate, right? So maybe that's a reason that we should be expanding the scientific method. I don't know. Okay, and then as per usual, I have got a large collection of sample questions for you to consider. Please do email me if you have any particular questions about these. Or you want to send me an example question that I can let you know how you're doing on, and then we can go from there. So this is the end of the lecture. I hope everything's been clear, and that's it for today.